Hello and welcome back to another episode of Math with Stone. Today we are going to continue talking about work in relationship to friction, and we got this guy pushing a fridge over here. And this fridge, we want to know how much work is done by this guy, and he pushed it with a force of 300 newtons. Okay, the refrigerator has a mass of 120. Well, that's a big refrigerator apparently. The coefficient of friction between the refrigerator and the floor is 0.2. The stick figure pushes the box, the refrigerator, a distance of 2 meters. Calculate the work done by said stick figure. Well, the stick figure was able to accomplish the work, which was a 300 Newton push, and it happened over a distance of 2 meters, which means he accomplished plus 600 Newton meters of work. All right, calculate the work done by friction. I'm going to run out of room for that. Part B, calculate the work done by friction. Well, friction is going to be force of friction times the displacement for friction, and that would be a negative force acting against it. So that would be negative 0.2 times the 120-pound fridge times gravity. So that's how you get the force for friction, times the displacement, which was 2 meters. And if we do that, we end up with negative 480. Okay? Newton meters. All right? So, part C. As the refrigerator moves across the floor, is it gaining or losing energy? Well, how can you tell? Well, how much work did we do on said fridge? We did 600 Newton meters, joules, and then the friction did negative 480. Did we win the battle over friction? And the answer to that is yeah. If we combine 600 with the negative 480, we have done essentially 240 energy added to this refrigerator. Okay, so it is gaining energy. All right, fun facts. Next one. A force of 70 newtons is applied to 20 kilograms. The object accelerates on a horizontal frictionless surface. The object starts at rest. Then how much work is done after 5 seconds? For this one, it's going to be a little bit more complicated. Okay? For this one, we want to know how much work is done for the first 5 seconds, but we don't know how far it has gone. And because we do not know how far it has gone, we can't even do force times distance. We need to figure out the distance first. We do have the force. We do have that 70 newtons, but we do not have the distance. We need to figure out the distance, and in order to do that, we are going to need to figure out a kinematic equation that will work. So kinematics, they are not going away. Pretty sure I spelled it wrong. Kinematics. All right? And one of the kinematic formulas that will work is that distance, the change in distance, is equal to your initial velocity times time plus 1/2 at squared. Okay, so initial velocity, it is starting at rest, right? Starts at rest. So the initial velocity is 0. So if the initial velocity is 0, this part's going to be like 0t, and it's going to cancel out. The distance would equal 1/2 a times t squared. So what is a? Well, we are knowing the time, and we can also figure out a as well, because remember, a is equal to, well, force is equal to mass times acceleration. Do we have the mass and do we have the force? We do. We got 70 is equal to mass, which is 20 times a. Could you solve for a? Yeah. You could divide by 20, and you could get 7/2 or 3.5 is equal to your acceleration. So we could plug that in. And we do have the time is 5. So we had a little bit of a hiccup for acceleration, but we can use every piece of information we have, which was the 70 and the 20. Anytime you have a force and a mass, you can figure out the acceleration. And don't forget your squared. All right, So if we solve this, you would find out that we have traveled a distance. If you do 1/2 times 3.5 times 25, 5 squared is 25, you end up with 43.75 meters. Great. Because this whole issue of not knowing how to figure out how much work was done was because we didn't know how far we have traveled. Well, we have traveled 43.75. If we plug that in, 43.75, you could do 70 newtons times 43.75 meters, and you figure out your work being done is 70 times that would be 3,063 newton meters, which is 3,063 joules. Okay? One more quick thing before we finish this video up, and that is going to be calculate the work using a force versus distance graph. Okay? Now, one of the things that might read here says, in the real world, the force pushing an object does not remain precisely constant and may change with time. Okay, so given force versus distance, the work done is the area under the curve. So I'm going to kind of explain what that actually meant. So let's say you're pushing something really heavy, like a car. Okay, in the beginning, you might have to exert a large amount of force or a small amount of force to get it moving. And that force might actually change as the object kind of like changes where its location. So maybe you're on ice and then you go to mud and it gets harder to push, or vice versa. So like it could have been easy to push, like in this case, and then hard to push at the end. Or it could have been hard to push in the beginning and then easy to push at the end. All right. If that happens, it's a little harder to find the work, and you find the area underneath the curve, which if you're in calculus can be found by taking the integral of the work versus distance graph. All right, force versus distance graph, excuse me. So if a lot of people think, well, why? Here's the force, 15, here's the distance, why don't I just do 15 times 0.2? That's because you weren't doing 15 this entire time. If it was 15 the entire time and then 0.2, you could do 15 times 0.2. If it's a rectangle, which makes sense because the area underneath a rectangle is just length times width. But this is not 15 the entire time. It was 0 in the beginning, 15 at the end. So in order to do this one, you need to find the area under the curve. You need to find the area of the triangle underneath that curve. So this would be 1/2 the base times the height, which in most of AP Physics 1, you will have some sort of triangle / rectangle combination. Normally they do like a triangle in the beginning and then they kind of go rectangle at the end or something like that. So what's the base? Well, the base is 0.2 times the height, which is 15. If we do 1/2 times 0.2 times 15, you would end up with, losing my answer, 1.5 joules of work being done during that time interval where we started doing very little, and then at the end we did a lot of force. Okay? That's going to do it for this one, and the next one we're going to be talking about power. Power, okay? So work versus power. See you then. Bye.